the estimation, the standard deviation, to do the following. We want to create an estimate of the variability of our distribution that resembles our normal distribution. So I like this graph, and I have shown this graph repeatedly, even to my graduate students. I go back to these slides and I show this because I like this graph. You basically have with the blue line, the blue distribution, that's a normal distribution, typically classical normal distribution. Each of these smaller distribution of smaller sample size basically show a different distribution. Obviously, they're smaller because the frequency is relatively lower because it's a smaller sample. But the distribution does also not really resemble a normal distribution. Only increasing the sample size gets it closer to resemble the normal distribution more closely. So with an increase of the sample size, you get an increase of this relative frequency and the increase in that center part of things, because this is where then the weight becomes. Because if the sample grows, you're not growing it on the outsides, you're growing it in the center, because that's just the most frequently occurring parameter. That's what the bell shape indicates. And when you look at this, keep in mind and remember that this is also reflected in our critical values, because when you take an alpha of 5% and you follow this column all the way down, you see that the distribution gets narrower and narrower, and it gets higher and higher in the center part, but basically the critical values get narrower and narrower because of this distribution, this relative distribution. And it comes from here starting with 12, a T of 12. With 30, you're basically down to 2.04. With 500, you're basically identically to the normal distribution of 1.96. And they're basically identically in infinity. So, and that's a little bit more conceptual. I know. I'm not qualified to talk about it.
But like, can one infinity be greater than another? Can one infinity be greater?
No. Infinity goes in both directions and basically will approach the shape of the normal distribution. And infinity will overlay it because it's extrapolating it towards that normal distribution. It's like the same concept as you have, for example, these tails that are moving from the normal distribution outside, they will never touch that x-axis. Only in infinity they will cross it. Arithmetically, the same concept as two parallel lines. They never cross, they only cross in infinity, mathematically. In infinity, which is an hypothetical kind of crossing, right? Exactly. Yeah, but let's not go there. I'm not qualified about advanced mathematics. I'm just a little data cruncher and biostatistician. Okay, so we have now so chapter 11. This table basically then, so this identifies these two first tests. Keep in mind the distinction is where does the standard deviation come from? If it comes from the population, you can utilize a set test. If it comes from the sample per se and you're estimating the population standard deviation, you use a t-distribution to approximate the normal distribution. If you have a paired sample t-test, and what will make you think paired sample t-test is basically a before and after condition. So basically you have the same sample at two different chronological conditions. You have 2 time points, and you basically have before and after, or you have month 1 versus month 6 situation. So that will basically prompt you to think of a paired sample t-test if you're meant to compare a sample population at 2 different time points. The way you approach this, and we have done this quite extensively, you calculate the difference from before and after. You utilize and you collapse it arithmetically basically to this one sample of different scores. So your comparison distribution is here the distribution of mean difference scores. And this is basically what you will be utilizing for your hypothesis testing. So basically you have a mean difference You have a variability of that difference scores, and you utilize this to estimate this distribution of mean difference scores. And by that, you basically utilize this to standardize your difference from 0 or whatever reference value you're interested in, to standardize this and calculate the test statistic. This is a little different from the independent sample t-test, where you have two independent samples. You have a population A and a population B. And now you're drawing these little subsamples out there, and you get differences between means. Your little subsamples, these pairs that you grabbed and then put back, and you just keep the difference. You get again a distribution of differences, but these are randomly sampled little samples that basically get you different difference estimates. These are the ones that you're basically using to standardize now your comparison distribution of differences between means. So this is arithmetically a little different, and it's a little bit more complicated, but it's not terrible. We've done it last class. It's really not terrible. So you calculate now a corrected variance for each of these samples. So you get two variances. The trick here is really that you need to get these two variances to merge them together in one pooled variance. And the way you're doing that, you're pooling that by basically calculating a proportion of the respective sample degrees of freedom to the overall degrees of freedom. And then you basically take the respective variance of each sample, and you basically put a weight on that, and you're merging them together. Then you have a pooled variance. That pooled variance, you basically, and we will do the exercise again today with an example that you have in your module. You're basically converting that then in a squared standard deviation by dividing these pooled variances by the sample size. Then you're adding them together. And then after square rooting it, you basically have a standard error of the mean that you can use to standardize the difference between your two sample means. And that's how simple that is, essentially. So these are the the four tests that we have done so far. This is how you distinguish them. And it really comes down to where's the standard deviation coming from, and are these two independent samples, or is this the same sample over 2 time points? That determines which test you're going to use. In addition to that, we discussed with independent sample t-test, the Bayesian approach to data analysis, which basically, if you read about a prior belief or a prior known probability, think of a Bayesian approach that basically will guide your decision making based on a prior belief, and you're not solely relying on one hypothesis test where you dichotomize your decision based on a test statistic. There won't be much questions. There won't be many questions on that topic, so don't worry about it. But if you know prior belief and that prompts you to think Bayesian, you know what needs to be known. Then we have, for the paired sample t-test, we talked about order effects. Order effects are important if you have an intervention that you're testing, be it like an exercise program, be it a wellness program, be it a weight loss program or whatsoever. And basically the order in which that intervention is being administered plays a role for the following period, that is your comparison period to which you're calculating that difference for. So if that order plays a role and the behavior or any other dynamic in the participant is being affected, then you basically are at risk for an order effect. The way you would counteract that is by counterbalancing. And counterbalancing is basically nothing else but, okay, so weight loss program, you have 6 months of weight loss program, then you have 6 months of observation period, which you have a mean during the weight loss period, then you have a mean during the non-weightless period. Obviously, the 6 month period after the weight loss period will be affected by the weight loss period, right? So you get a different estimate if you, as compared to not having a weight loss program first and then having a weight loss program. So that's this order effect. So the way you can counteract this by basically taking 50% of your population that starts with the weight loss program and 50% of the population that starts with the non-weight loss program, and then cross over respectively. If you randomize them in which participant starts with which period first, then you're counterbalancing. That's a randomized crossover design. That's one way of counterbalancing that is most intuitive. So order effect and counterbalancing, these were additional topics we discussed. I did start recording, right? Yeah, okay. And for the single sample data, we did not talk about anything in addition. Good. Know how to interpret 95% confidence interval in this context. So if you're calculating, and this is the example, I forget the example we had for the single sample t-test, but basically make sure that you understand you need these critical values to determine the 95% confidence intervals, or if you have a 90% confidence interval, know where to find that in the t-score table. If you have a 90% confidence interval, you need to find the respective column in your t-score table, and that becomes a critical value now. So basically you see that the 90% confidence interval is basically narrower because you're less likely to capture that population mean. If it's wider, it becomes a 99% confidence interval, which would be here. And that's wider than the 5% alpha. Also of note, and that was there was a question actually that somebody asked me that question. The distinction between an alpha level and a p-value or a p-level. Strictly spoken, an alpha level and a p-level or p-value is not the same. The p-value is the actually calculated probability of a type 1 error to occur with your sample, with the known difference, your sample size, and the calculated test statistic. Whereas an alpha level is a set and predefined p-value, p-level that you're willing to accept with your analysis. So they're actually conceptually something different. I don't know who asked me this question. There was definitely one in the F class. One of this class also asked me that question. Conceptually, they are the same. On the quiz, I would give you the points because the question was phrased in a way that it really didn't make a difference in essence. So it was right in both aspects. But conceptually, just know that there's a difference between an alpha and a type 1 error probability, a p-value. Good. What else? Okay, so this was this. No, the 91% confidence interval, no effect size. We've talked about the effect size. Effect size is basically that difference between mean 1, mean 2, or the differences between condition time point 1 and time point 2 compared to 0 to no change, divided by the standard deviation with the aim to take sample size out of the equation and kind of put weight back on the actual difference and the variability and less on that sample size. With the emphasizing the problem that with large data sets and large sample sizes, you're quite likely to get a significant difference, which can, in the greater realm of things, not mean much because it's just affected by the sample size, because the sample size will diminish the variability arithmetically. Calculation of the standard error of the mean will result in a smaller standard error of the mean, which in essence is not correct and doesn't really help you because the actual clinically or meaningful difference, the practical difference, is not as meaningful. So therefore, the effect size does have quite some importance. And it's always important whenever you do a comparison using a t-test or a z-test for that matter, to always keep in mind, is this difference that I'm observing, that I'm seeing, is that really practically relevant? If I, for example, if I see in the whole class, let's say a difference in the exam scores of all my students from exam 1 to exam 2, and that difference is 2%, and I have a large class, that may not have made much difference in the greater arm of things. But then I need to keep in mind, okay, so what is that difference, taking the sample size out of this equation? The same conversation we're having quite frequent when it comes to large data sets in my day job, so to say. If we have a blood pressure change of 1 millimeter Hg or an increase of 1 grams per deciliter of glucose in a population of 100,000 patients, that doesn't really change the world. So that was not a good intervention, or not a clinically meaningful intervention. So it's to be kept in mind. Good. Practical relevance, statistically significant difference. Good. So now we have, for today's class, we have a practice lab. And so we have, bless you, we have 3 PowerPoint presentations. So these are the 3 slides, slide decks. Then we have 1 Excel spreadsheet, practice lab 3. We have 1 R code, which is practice lab 3, the R code, and we have a t-distribution table on the module. We are doing 2 different tests. We're not going to go back to do a 1 sample t-test. So now I'm giving away already what tests we're going to do. We're going to do a quick paired sample t-test. We're going to repeat this in R, just so you see how the output is going to look like. Because you may never use R, you may never code it, but what you certainly will see, and I'm quite certain on that, somebody will do analysis for you if you further your academic career. Somebody will do analysis for you, and you will see a statistical output. And this is part of the exercise of the practice labs. I want you to have seen those once in your life. And for the t-test, it's quite intuitive. For some other tests which we will do, it may be a little less intuitive. But I think it's a good exercise to have seen those. Good. Okay, so we have here the example that we have 8 students that completed 2 different exams. We have exam 1 and exam 2. So it's the same 8 students. So the comparison distribution, we know already it's 8 students, 2 exams, 2 time points. It's a before and after situation. It's basically a paired sample t-test. The comparison distribution, therefore, will be the mean between difference scores. The way you would approach this is by calculating a difference from exam 2 minus exam 1. Gets you basically the change over time. Then you just need to calculate an average.
Where is that? Yeah, where?
On the module 15.
The first one. But it says TV fiction and documentaries.
That is 11.29.
Oh,
You change the worksheets down here.
sorry. Thank you.
That's okay.
It automatically
Found it?
goes to the last one. That's it.
Yeah, it always does. Wherever I close the spreadsheet and saved, that's what it basically will display.
Got it. Do you mind repeating that?
Well, you just create a difference. You do exam 2 minus exam 1, and you put this down. And then you do the average between this difference. That gets you an average. Then you can do a standard deviation. It's STDEF. STDEF is 5.7. So, okay, so we know the comparison distribution. We know the populations that we're investigating is the 8 students. We know the assumptions, normal distribution, randomly sampled, and they are independent from each other. So now we need a null hypothesis. So our HO is here, exam 1 minus exam 2 equals 0, right? HA is exam 1 minus xm2 is unequal to 0. Yeah. So that's how you would phrase your null and the alternative hypothesis. That's step number 2. I forget those steps. Okay, so we're basically going to paired sample t-test, chapter 10. Step 1, populations, distribution assumptions. Step 2, state null and research hypothesis. Now step 3, determine the characteristics of the comparison distribution. That's basically where you know your standard deviation. You know how that standard deviation of your differences looks like. You have calculated it. Now you need to know, based on this one collapsed sample, you know the mean. How much, if you had a sample of the very same size, how much would the mean estimate vary around that one mean that you have at your disposition? Therefore, you need to calculate the standard error of the mean. The standard error of the mean is calculated as the standard deviation, 5.7, divided by the square root of the n, which we know is 8, right? Gets us essentially a standard error of the mean of 2. That means, so the interpretation of this is that, yes. On the what?
On the clarification.
This one?
Yeah.
It's right here. You're welcome. Okay, so the standard error of the mean. So we basically know now that if we have this one mean, and we assume this to be our population mean, we know that samples of the same size, another 8 students from somewhere from that population gets 2 exams to do. Their mean estimate is likely going to be 68% of that population are going to be within +2% or score and -2 from that mean. That's where the population principle applies, right? So now we have a standard error of the mean. That's the characteristic of our comparison distribution. Now we need a critical value, and that's with a sample size of 8, a corresponding degree of freedom of 7, because degree of freedom is n sample size -1, because we're preserving the relationship between the variable of each individual score and the sum of squares, but being able to drop 1 in this estimation of that variance, which is redundant because it can be recalculated by knowing the sum of squares and all of these individual entries minus that 1 that we don't need. So degree of freedom is 7. With a degree of freedom of 7, the critical T is 2.36. 2.36. If we know a critical value, if we know a critical T, we can now easily calculate our 95% confidence interval, which gives us, in the greater scheme of things, an estimate of our cutoff values. Yes?
Can you just go quick on the standard error?
The standard error?
Yeah.
That is.
But for the one next.
This one?
Yeah.
That is this formula.
Okay.
Divides the standard deviation by the square root of 8.
Okay.
8 is the sample size. Yeah. So the critical value of 2.36 allows us now to calculate 95% CI. With 2.36, we would calculate the lower limit and upper limit. Lower limit is our average minus the critical value multiplied by our standard error of the mean. Gives us minus 3.49. The upper limit equals 1.25 plus critical value 2.36 multiplied by the standard error of the mean. gives us this interval, which basically contains our 95% probability of capturing that population mean, or the reference value that we're basically after, which in our case, in a paired sample t-test is 0, because we're testing against a null hypothesis of 0. So since 0 is within the 95% confidence interval, we already can say by the naked eye, just looking at that, we can already say the null hypothesis is not going to be rejected at an alpha level of 5%. Yeah, that's actually an alpha level of 5%.
How did you get the 2.00 on Excel?
With this formula. That's standard deviation divided by square root of the sample size.
Which is 8.
So C14, if you have the same cell as I have, that's this guy, standard deviation C4 to C11. That gives you the standard deviation divided by the square root of the sample size, gives you the standard error of the mean. You're welcome. Good. Now we have, okay, next. So we have the 95%. Kind of a confidence interval, we know not the critical value, the cutoff. So critical value or cutoff, that kind of means the same thing. Now we calculate the test statistics, so we need now our t. So the t is here calculated as our difference. So this is exam1 minus exam2. In our case, exam2 minus exam1 minus 0. Oops. Minus 0 only because this is our null hypothesis, right? You don't have to really subtract the 0 because it's like, yeah, subtracting nothing from a number is obviously still the number. Divided by the standard error of the mean, that's 2, gives us a t of 0.62, right? Simple. Good. What are we going to do with this? We're making a decision, and the decision is we are not rejecting our null. Because our t is not exceeding the critical t, the 95% confidence intervals contains our null hypothesis reference value of 0. Simple. So now I want to bring this into R.
Can you go back to
Sure. Yes.
I got a negative number for the 0.622.
You likely subtracted exam 1 from exam 2 rather than exam 2 from, yeah. Does make a difference. It does not make a difference, so you can leave it at that. R is, so since it's a symmetric test, it doesn't make a difference. It's just, as I mentioned with the paired sample t-test, it makes it conceptually easier to subtract it that way, because if you do 2 minus 1, if it goes down from exam 1 to exam 2, it gives you a negative sign. It's just more intuitive because it was a decrease and it's negative. If you do it the other way around, a decrease becomes positive. It's conceptually, I'm trying to minimize in my thinking always that I try to choose the pathway that confuses me less down the road here. If you do it that way, it may lead to confusion down the road. Yes.
Do the LL and
The LL is the lower limit of the confidence interval, and that is calculated as standard error of the mean. It's basically, no, wrong. It is the mean, the 1.25, minus the critical value of 2.36, multiplied by the standard error of the mean. It gives you these bounds in which you're 95% confident you capture the true population mean, or you quantify the probability of this basically reflecting your reference value. Good. Okay, R. So R is doing this quite simple. So you basically you have first line, get environment, that's just a node that's hashtagged. Everything that's hashtagged is basically not running at all. It's just a node to self. Line 2, the RM, we know that that command already, that basically is just emptying the environment, kicking everything out that shouldn't be there. Your line should actually look like this. Line 6 and 7 creates a data frame. So the data frame command df1 equals data frame basically creates a data frame with two variables, exam1 and exam2. The C here, that concatenate, is basically just giving you a list of numbers. So all that you're basically doing is like, you have this list of numbers, that's the C and the bracket, it's just, it tells R is like, hey, there are a bunch of numbers coming. So you're basically, these bunch of numbers are basically packed into this variable. So this is how you create a data frame. A data frame with two variables contained exam1 and exam2. And if you inspect this data frame, if you inspect df1, you get exactly that. So it contains two sub objects within the object, which is exam1 and exam2, that you now can utilize in line 12 to calculate a paired sample t-test, and that's the t-test command. So pay attention that this paired equals true. So you need to tell R that it's a paired sample t-test. Once you do that, it basically gives you a paired test. And this is that statistical output that I was talking about. So you basically have paired t-test. The data is from exam1 and exam2. It gets your t-score, which is the same t-score that we have calculated. It knows that it has 7 degrees of freedom. It gives you a p-value of 0.5531. It gives you an alternative hypothesis so that the true difference in means is not equal to 0. It gives you a 95% confidence interval, and it gives you mean difference. If we're going back to Excel, if we were to calculate the p, we would do t-test of array 1, array 2, two tails, and paired, we get the same t-test, 0.5531. Same concept, different approach, different method, it's different tool. It's actually same computation, different tool. So line 14 basically takes now this t-test command and packs it in a different object. So this object is not t-test df1. It does nothing else but creating an object, labels that object t-test df1, and just basically puts that t-test in that object. If you run that line, the resultant is basically t-test1. It basically shows the same thing. It just becomes a permanent thing because everything you will do from now on, the input in here will be the same. If you go deep into coding, that may be relevant for you right now at this point, not relevant. I just wanted to show you that's how easily you can put things into objects, and you can save them, you can store them within that object. And then you can query them. You can basically, you can ask, with ls, you can ask R, what is contained in that thing? So for df1, for example, you have various things in there. We can look at this in a little bit more detail by clicking on the magnifying glass here on the right side. We're basically seeing here what's contained in our t-test. So that object that we've created is basically having here, so we have the data contained. We have the statistic contained, which the t is here 0.62, which we know. That is our degrees of freedom. That's our p-value. That's our confidence interval. That's our estimate. That's the difference. That's the null value. the reference value, that's our standard error. Alternative, which you can change to one-sided if you're interested to do so. Method is paired t-test and the data name. You can query each of these individually. You can query these individually by addressing p-value individually. For example, you can do t-test, and with the $sign, you can always get individual sub-objects out of an object. If you want the confidence interval, you can get the confidence interval out. So you can do confidence interval 1. That would be the lower limit. Confidence interval 2 is the upper limit. If you want to put this together, you can do this too. So I did this with the other class before. Don't worry, but it's just to show you how you can actually automatize this. So now it gives you like lower limit to upper limit. And you can hypothetically, you can utilize R with various additional tools. You can utilize this to create automated reports. So if you have data and you're reading that data into R, and then you want to put this into a report, R will automatically generate the report for you, will adapt values like the confidence intervals to your current calculation, and then just export it as a PDF, and you can automatically send it off to your boss or to your collaborators or whatsoever. So R is quite versatile in that regard. Line 22 basically gives you here an effect size, which we haven't calculated yet in the Excel example, but we know that the effect size is calculated as the difference divided by our standard deviation. And that gives us here 0.22, which is, despite its lack of significance, and the t-score that is smaller than the critical value, gives us a small effect size. That emphasizes the importance of the sample size, because if we were now increase our sample size to 1,000 and our degree of freedom to 999, we're basically looking at the standard error that is standard deviation divided by square root of our degrees of freedom. And if we utilize this to now calculate our t, this is now the difference divided by our standard error of the mean. This gets us a t of 6.96, which is exceeding our critical, with a sample size of 1,000, we have a much smaller critical value, which is 1.96, just like the normal distribution, the set score. So the critical value also changes. And we see now that the t is exceeding our critical value. Therefore, we will reject the null hypothesis at a larger sample size, emphasizing that when you increase the sample size, your variability will be smaller, and therefore your standard error of the mean will be smaller, because you get a more accurate estimate of your population mean. And thereby, you're more likely to reject the null hypothesis and less likely to accept the null. So now we're rejecting. Good. Simple, right? And now we're doing the same exercise here again with, but now we can do it faster. So HO is again score 1 minus score 2 equals 0. The HA is score 1 minus score 2 is unequal to 0. We can now continue to calculate standard error of the mean, which is here the difference. This is now this minus this. And we can calculate average and standard deviation. Oops. STF. So now the standard error of the mean to characterize our comparison distribution equals standard deviation divided by square root of our sample size, which we know is 1, 2, 3, 4, 5. Square root of 5 gets us 2.75 as our standard error of the mean. And with a critical value t for a degree of freedom of 4 with 2.78. We can now easily calculate our t, which is minus 7.8 divided by the standard error of the mean. It's 2.84, which we see is greater than the critical t. Therefore, we will reject the null hypothesis. I'm not going to go into the details because now we have done this quite abundantly. So, but we can do this now in R. We're basically looking at 10.20, that's line 25, or I think for you it should be 24. So we are building now df2 as our data frame. If we click on it here on the right side, we can basically look at the data frame. So we see this value here in a more X-like format. We're running the same line of code, basically running the same analysis, gets a score 2, and t-test is here 0.047, which is smaller than our alpha of 5%. That's line 30. For you, it should be 33. We can again extract the confidence intervals, which are the same that we calculated in Excel. And then we can look again at the object of the t-test. Sorry. Now the object is basically the t is 2.84, just like we calculated. It's larger than the critical t of 2.78. With degree of freedom of 4, we have a p-value of 0.047. And the confidence interval identical to what we calculated. If we want to calculate our t-test, we're basically getting a p-value. We can do this with t-test. Score 1 for these 5 individuals as array 1. Score 2 as array 2. 2 tails and 1 for paired. Gets us the same p-value as in R. So that's how easily that could be calculated. Okay, any questions to any of this? It's considerably simple, right? It's a little skeptical look. No, it's basically it follows the same outline. It's once you understood the concept, you kind of will have no problems to replicate it. It's just you need to have done it yourself, and I believe in that. And I think there's merit in kind of doing these computations at least once yourself to kind of have thought through it and have kind of memorized it by doing it yourself. So that's the idea of the homeworks in essence. Okay, so now we have a little bit of a different example. So now we have an independent sample t-test. So now we have 2 independent sample population. So the example here is that if you watch fiction on television, like Mad Men or The West Wing, you're more likely to be able to understand expressions in people's faces compared to those that have watched documentaries over the period of 36 hours. No, over half an hour. Okay. So they were asked whether they could decide whether persons were jealous, panicked, arrogant, or hateful on scores between 0 to 36. So basically getting 1 point for each guessed emotion correct. And we have here on the left, we have 2 variables. We have TV fiction and documentary. So these are two different samples. We have here 3, 6, 9, and we have 3, 6, and 8. So now independent sample data is calculated slightly different, as you remember. So now we have two samples which we have to deal with in some shape or form. So we have TV fiction and we have documentary. So firstly, we want to calculate our n's. So we have 9 and 8. Then the degrees of freedom, that is 8 and 7. Then we have a degree of freedom total, which is basically the sum of 8 and 7, which is 15. Then we need means. So that the average is here 29 of TV fiction, and then the average for documentary is here 27.5. Then we need a standard deviation. So let's push this maybe a little over. Okay, so here we have an average, we have a standard deviation, and then we have a variance. So here we have the standard deviation STDEF. Then we have a standard deviation for documentary, which is smaller, despite it being a smaller sample size. A smaller sample size, you would expect actually a larger deviation. If you calculate the variance, you're basically getting a larger variance, or a smaller variance. Okay, so now we want to know, so we have now our, so remember how we calculate now our pooled variance as we need for the independent sample t-test. We need to take our individual variances for both samples. We need to create weighted variances, merge these two weighted variances together to a pooled variance, and then utilize the pooled variance to calculate our actual standard error of the mean. So now we have our proportion. Our proportion is here 8 over 15. And it is 7 over 15 for degrees of freedom total. So now we need a weighted variance. The weighted variance is calculated by the respective variance in the group multiplied by its weight in the overall degrees of freedom. Equally for the second group multiplied by that proportion. Gets us 0.66 and 1.2. Pooling this together is basically the sum of these two, right? Once we have a pooled variance, we're basically calculating our S squared difference. That's our variance for both added together. We're basically now adding this and this. That's just 1.86. Oh, sorry, late. 1.86. We take the pooled variance and we're dividing it by the square by the non-square rooted, because we are on the variance levels. We're dividing it by the sample size. We're adding a second pooled variance divided by the second sample size. Gets us to an S squared difference of 0.44. Now an S difference, which is the standard error of the mean that we're actually looking at, because this is how we're standardizing our our differences between means, is square root of that 0.44, gets us to an S difference of 0.66. So now it's simple. So we have a critical T that is of a total degrees of freedom of 15. Keep in mind, and this is a little bit of a catch, So if you calculate the degrees of freedom, you calculate it for each of your sample populations individually. So if you have a paired sample t-test, you have before and after, but your actual comparison distribution, the degrees of freedom, is based on one variable only, on one sample only, because it's the same individual before and after. If you have an independent sample t-test, your critical value is based on the overall degrees of freedom, but you have two different sample populations. And you need to make sure to calculate 2 degrees of freedom. So you're basically calculating of your 2 samples, the overall sample size, which is 15, but you need to take the degrees of freedom of each individual sample. So it's 15 minus 2, and that's a catch. So always each variable needs to be treated independently. For the paired sample t-test, you collapse it to the difference only. That's why you only have 1 degree of freedom. For the independent sample t-test, you do not do that, but you treat them both independently. Therefore, you have 2 degrees of freedom. So that's a catch, because now the critical value is here 15 minus 2. Oh, it's actually 7. No, sorry, it's 17. It's 9 and 8 is 17. Sorry. So degrees of freedom here is 15. So your critical value here is 2.13 for an alpha of 5%. 2.13. So if I calculate now the t, this is basically average 1 minus average 2 minus 0 as our null hypothesis, divided by the standard error of the mean difference. So the t is here 2.25 or 2.26, which is larger than the critical t. Therefore, I reject the null. Make sense? Let me put this formula to the side. So again, you're calculating your degrees of freedom for each of those groups. Let's go a little up. So the catch I was talking about is that you need to calculate degrees of freedom for each of your groups, for each of your samples. So 9 becomes 8, 8 becomes 7. The total degrees of freedom is 15. You come then to basically calculate the contribution of each sample to the total degrees of freedom. So you calculate the proportions, 0.53 to 0.46. Then you calculate the weighted variance. That's the variance you calculated for each of the samples. You take the 2.25, you multiply it by your proportion, and you calculate kind of this weighted variance, this aliquot. Then you take the second variance, you multiply it again by your proportion, you get this weighted variance again. You're adding them up and you have a pooled variance, accounting for the variance in both samples. So you have an overall estimate of the variance. Then next, you're adding both up, but you're accounting for both. You say both are contributing some form of contribution to the variance. So there's 2 pooled variances I need to take into account, but they will be adjusted or calculated as an estimate of the individual standard error of the mean, because you're calculating the differences between means. So that's your comparison distribution. And you're calculating this for each of them by dividing each of them by the sample size to calculate that standard error of the mean. So both of them will be divided by the sample size. And will basically leads to this equation. So this is basically when you remember the standard error of the mean, that's how you calculated it. You have the standard deviation divided by your square root of the n. Now you have a pooled variance, that's F10. And you're dividing it by the sample size rather than the square root of the n, because squaring a square root gets you the actual number, right? So this is what we're doing. We don't need to square root this. Accounting for this both individually gets us to this estimate of our squared standard error of the mean. And then essentially down to the level of after square rooting it, that's our standard error of the mean, of the comparison distribution. So that's the characteristic of a comparison distribution. With a critical t for the degree of freedom of total, gets us then to compare our calculated t to lead us to rejection of the null. Okay. Any questions? It's conceptually a little trickier. I'm well aware, but it's if you follow through step by step, it becomes quite intuitive. Okay, R. Oop, running out of battery. So I would make it through 2 classes. So when we open R now, we have here on line 30, should be 38 for you. We have to calculate the development of data from 3. So that's basically 9 observations. We can now calculate the respective means. That's line 49 and 50. A little caveat. So here is an addition to the mean equation. That's NA.Rm equals true. What does that mean? NA's R does automatically fill missing values with NA. That is in essence nothing else but telling R, look, calculate the mean for me. If you find any missing values, remove them. RM stands for remove. That's all it is, because there's one missing value because the unequal sample size. So if you have standard deviation, same story, we get the same value as in Excel. And now we're just doing the same t-test that we have done in Excel. Took us a little long in Excel, right? So we have now a t of 2.29. The degrees of freedom, notably, this is only an approximation of the 15 that we have. Why is that? Because so the degrees of freedom and the modification of our variance estimate is basically an approximation. Everything is an approximation. So what R is doing, it utilizes the actual mathematical function and approximates by adapting the mathematical function of that respective t distribution curve to that of a normal distribution curve, and gives us an estimate what's the modification of the variance estimate would have needed to be to result in a perfect approximation of that normal distribution curve. It's more accurate than what we do. That's pretty much what it comes down to. So it basically takes the mathematical function and it's just precisely really reflecting the normal distribution curve and gives you the exact estimate. So we use the imprecise way of like eyeballing it by saying, okay, so it's 70 minus 2, that gives us 15. R is doing the fancy approach, basically modeling it out on utilizing the mathematical function to estimate that degree of freedom that would have been needed. The p-values, Excel is doing the same, it just doesn't tell you that. The p-values is exactly the same as we would have calculated in Excel. Let's just quickly do that. So that's our p-value in Excel. That's t-test, array 1 and array 2. Array 1, array 2, And now it's getting a little tricky because now we have the tails. So this is two tails. It's a two-tail distribution. And now we need the right option. So we have paired two sample equal variance, homoscedastic, or two sample unequal variance, heteroscedastic, and we're going to do 3. And that gives us the same p-value estimate of possibly seeing a type 1 error. It's the same value as R is giving us here. So if you walk in this, so we have all these values here for the Wilks 2 sample t-test. The Wilks 2 sample t-test is basically nothing else but a 2 sample t-test unequal variance. So we have a t that we have reproduced. We have a degree of freedom that is like somewhere close to that eyeballing estimate that we do. We have a p-value consistent with Excel. We have a confidence interval, which we know how to calculate in Excel, and we have mean estimates that are consistent with what we would have estimated in Excel, or what we did estimate in Excel. So we can quickly do the 95% confidence interval, and we know that's super simple, right? So 95% CI, that's an LL, UL. So it's basically, it's the difference. It's this minus this minus our critical t multiplied by the standard error of the mean, which is 0.66. That's our lower limit. Then we do, oops, E13 minus C13, D13 minus C13 plus our critical t multiplied by standard error of the mean. So that's basically the same 95% confidence interval that XR gives us, and basically indicates already it's not containing 0. Therefore, it is a significant difference. Okay, please make sure that you have R finalized. The way you're basically submitting the practice lab is by clicking in the R console, left lower quadrant, pressing Control and L. Then clicking in the script, pressing Control and A to selecting everything in the script. Then you press Control and Return to run the entire script. Next, you select everything that's in the console and make sure that you selected everything. You make a right click on that, you click Copy. You go on Spotlight, you find Text Edit. You create a new document. You copy paste everything that you just ran. You go and save. You go into Practice Lab 3, the folder that you have created in your statistics folder, STAT1021G, your family name, Practice Lab 3, and save. And that's all you need to do. You submit it via Canvas. Deadline is next week on Wednesday. Any questions? No? All right. Then thank you very much. Have a nice evening.
Thank you.
I was running a bit late because I came from my last class, so I was marked absent. Is there any way you could fix it? Because I was here.
Yeah, is it where I can?
Sierra.
Was here, yeah.
Thank you.
Got it.
I know that. I can't do it. No, I actually, I'm helping.
So I was trying to do the
Oh, nice. Okay.
confidence interval, but I got this number instead of what you got.
That is interesting. You're not subtracting it.
Is that right? Oh,
No, you
I thought you're subtracting and then
have your minus 27. Huh?
oh, I don't know.
What's a minus?
I don't know.
No, where is it? Let's get to the bottom of this. Ah,
Yeah.
that's a minus.
Well.
Oh, okay, right.
No, it should be fine. That's why you get double this.
Oh, that's right. Okay.
Yeah.
Like, they're related, I'm just making sure you're marking present.
Yep.
Bella Rudoy.
Bella. Oh, somebody told me you would come.
Yeah.
I trusted the process.
Okay, thanks.
good.